Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Module 046, Oscillators. Please follow me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@NdinechiMichaelC. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. I would like you to listen to related lectures, as this lecture is part of instrumentation and measurement. You can listen to my earlier lectures on theory of electronic instrumentation and measurement. You can also listen to my earlier lecture on statistical error in measurement and instrumentation, and of course, we have also treated electronic measuring instruments. So you can see these lectures going to my channel, Engineering Lecture Series, and listen to them so that you can follow up in this present one, which is oscillators. Also, you can visit Ebony Educational Consult website at www.ebonyeducationalconsult.com for more engineering lectures. Now, let's introduce our lectures today. Instruments that generate signals are widely used to provide test signals that can evaluate the performance of electronic systems. There are various types of signal sources depending on the type of waveforms required and the frequency range. The term oscillator is usually used for a signal source that generates only sinusoidal waveforms. We say usually used to denote those signal sources that generate only sinusoidal waveforms. The term signal generator is used for signal sources that not only generate sinusoidal waveforms, but can also be used to modulate a signal. It is important that as a student of electronic and communications engineering, you notice the differences when somebody mentioned oscillators, when somebody mentioned signal generators, and when somebody mentioned function generators or even synthesizers. So we say the term function generator is used for instruments that can provide a variety of different shapes of waveforms, such as sinusoidal waveform, square wave waveform, pulse train, triangular, and sawtooth waveforms. Again, you will be hearing of synthesizers, and we say that synthesizers are oscillators in which the signal is built up digitally. Now, let's look more on what is an oscillator, because we said there are those circuits that really generate sinusoidal waveforms. So, oscillators are electronic circuits that generate an output signal without the necessity of an input signal. It is very important that you note this, that any electronic circuit that generate an output signal without the necessity of an input signal is an oscillator. They produce a periodic waveform on its output with only the DC supply voltage as the input. The output voltage can be either sinusoidal or non-sinusoidal. A basic oscillator block diagram is as shown in Fig 1. If you look at that Fig 1, you see that it's like a closed loop. You have the oscillatory circuit, which is just a circuit with a DC supply. Then amplifier, which helps to amplify the signal until it reaches the desired level. We will see how all this is carried out. Then, in most cases, there is a feedback which helps to regulate and stabilize the output. We will see, as we go down, we break down these two block diagrams so that you see what is happening. But if you look at this block diagram, you see that there is no input, but there is an output. So any electronic circuit that gives output without the necessity of an input is termed an oscillator. So these oscillators can be classified into two main categories as follows: the feedback oscillators. Now, in the feedback oscillators, the oscillator returns a fraction of the output signal to the input with no net phase shift, thereby resulting in a reinforcement of the output signal. If you look at Fig 1 above, you see that there is a feedback loop where the output is fed back to the originator of the signal, which is the oscillatory circuit. So we say that with that, it reinforces what we now call the input, even though it is not an external input to the system. After these oscillations have started, the loop gain is maintained at unity to retain oscillations. Because if you look at that, when the output is fed back, it boosts what is coming. So the next output is expected to be higher than the previous one. So if you allow that, then the oscillation will not be maintained at a particular level. So for you to maintain that oscillation at a particular level, then you start doing certain things. Those things are what we are going to gradually and simply explain so that you understand exactly what happens. So the first thing is that the oscillations, after oscillations have started, the loop gain is maintained at unity to retain oscillation. We have said there will be no net phase shift. I'm sure you know what phase shift is. Then the oscillation will have to be retained at unity, that is gain, unity gain. So a feedback oscillator consists of an amplifier for gain, as we've seen in Fig 1, and a positive feedback circuit that produces phase shift and provides attenuation as shown in Fig 2. Now, let's look at Fig 2. You see, you have a circuit amplifier which have a feedback circuit, and the feedback circuit produces attenuation and phase shift. So we have seen from the first one to a step further that this feedback we saw in Fig 1 produces attenuation and phase shift. We will concentrate more on these feedback oscillators in this lecture and our next lecture. Then subsequently, we will talk on the relaxation oscillator, which is the second segment of these oscillators. So say the second class of oscillators is the relaxation oscillators. Here, instead of feedback, the oscillator uses an RC. When we say RC, resistor capacitor combination, so uses an RC timing circuit to generate a waveform that is generally either a square wave or any other non-sinusoidal waveforms. Typically, these relaxation oscillators use what is known as Schmitt triggers or other devices that change states to alternately charge and discharge a capacitor through a resistor. Please subscribe to my YouTube channel so that when in the next two lectures, when we treat Schmitt triggers, you will see exactly how it works, because it is a very important circuit used in signal conditioning. Now, let's look at feedback oscillators. Remember, we said two types, the feedback ones and the relaxation ones. So let's quickly look at the feedback ones. Feedback oscillators operation is based on the principles of positive feedback. We may not go into details what positive feedback is, but we know that we are supposed to know by now what positive feedback is. They are widely used to generate sinusoidal waveforms. We have said that. In the positive feedback, a portion of the output voltage is fed back to the input with no net phase shift. This helps to strengthen the output signal as illustrated in Fig 3. Here, the in-phase feedback voltage is amplified to produce the output voltage, which in turn produces feedback voltage. That is, a loop is created in which the signal maintains itself and the continuous sinusoidal output is produced. Now, look at this Fig 3. We see the amplifier that has a gain AV. We have the feedback circuit, which introduces attenuation and phase shift. Now, if you look at the signal coming in, you see the two arrows showing the in-phase signals. You see that what is coming into the amplifier is in phase with what is coming out of the amplifier. Now, the amplifier has a gain. That is why the amplitude of the signal coming out of the amplifier is higher than the one going in, but they are in phase. So a portion of this signal coming out from the amplifier is fed back through the feedback circuit, where it passes through some level of attenuation and probably phase shift. Then that is fed back as VF to the amplifier. So say that is the principle of it. Now, this amplifier is non-inverting. When we say non-inverting, it means that the phase of the output is the same thing as the phase of the input. Now, say that the other condition is a loop is created in which the signal maintains itself and a continuous sinusoidal output is produced. This phenomenon is called oscillation. In some types of amplifiers, the feedback circuit shifts the phase, and an inverting amplifier is therefore required to provide another phase shift so that there will be no net phase shift, because that is a condition for oscillation to take place. And this is illustrated in Fig 4. So if you look at Fig 4, you see out of phase signals, the arrow pointing to out of phase signals. So I want you to confirm that you know why the signal on the left, which is drawn in red, is out of phase with the one after the amplifier, which is drawn in black. You see that their phase is different. So we are saying that when an amplifier is an inverting amplifier, then it means that what you have will be, what is coming out will be out of phase. So you needed an inverting amplifier so that by the time that signal is fed back, it will invert it back to what it's supposed to be. So say that in some types of amplifiers, the feedback circuit shifts the phase, and an inverting amplifier is required to provide another phase shift so that there will be no net phase shift as illustrated in this Fig 4. So if you look at it and compare with the Fig 3, Fig 3 we say it makes use of non-inverting amplifier, while this makes use of inverting amplifier to make sure that the phase shift is restored to what it should be. Now, there are conditions for oscillation to take place. For oscillation to take place, two conditions must be satisfied. We say that one is that the phase shift around the feedback loop must be effectively 0 degrees. There will be no net phase shift. The second one is that the voltage gain A around the closed feedback loop must be equal to unity, must be equal to 1. So this is illustrated in Figure A and B, Figure 5A and B. The voltage gain around the closed feedback loop, call it A closed subscript closed loop, is the product of the amplifier gain, AV, and the attenuation, beta, of the feedback circuit. Therefore, A closed loop must be equal to the gain, the voltage gain, multiplied by the attenuation. Look at this figure, you see that you have an amplifier there, then you have the feedback circuit, which is giving phase shift equal to 0. Now, if you look at the signal that is coming, the arrows, and look at the signal that is coming to the feedback circuit, you see that what is coming out, the same signal coming out, is in phase, but because the circuit has attenuated it, in the diagram, we show it as being smaller than the one coming in from the right. So, see that there will be no phase shift, but that circuit, that block in green produces some attenuation. That is why the signal output is lower a magnitude than the one coming in. So in the second figure, the 5b, we say that the closed loop gain must be equal to 1. So now, if you see, we repeated almost the same diagram, but here the feedback is talking about the attenuation. Even though the signal is still in phase after leaving the feedback circuit, but it has been attenuated. So for oscillation to be sustained, this closed loop gain will be equal to the gain of the amplifier, which is AV, multiplied by the attenuation, beta, must be equal to 1. So these are the two conditions. No net phase shift. The phase shift must be equal to 0 degrees, whereas the closed loop gain must be equal to unity. Now, if a sinusoidal waveform is the desired output, a loop gain greater than 1 will rapidly cause the output to saturate at both peaks of the waveform, thereby producing unacceptable distortion. But we will see where this becomes useful anyway. To avoid this, some form of gain control must be used to keep the loop gain at exactly 1 once oscillations have started. For instance, if the attenuation beta of the feedback circuit is 0.01, then the amplifier must have a gain of exactly 100 to overcome this attenuation. Else, the level of distortion that will occur will be unacceptable. Now, how does this oscillation start? Recall that we say that there is no input signal. Oscillators are electronic circuits that produce output without the necessity of any input signal. So, how does this oscillation start? So we say, for oscillation to begin, the voltage gain around the positive feedback loop must be greater than unity. You can see, we say for oscillation to be sustained, the voltage gain must be equal to 1 unity. But we said for it to begin, the voltage gain must be greater than unity, so that the amplitude of the output can build up to a desired level. The gain must then decrease to unity so that the output stays at a desired level and oscillation is sustained. This is illustrated in Fig 6. From the figure, oscillation starts at time t0. The condition, closed loop gain, must be greater than 1, causes the sinusoidal output voltage amplitude to build up to a desired level. Then, when it gets to the desired level, the system is designed such that the closed loop gain, ACL, decreases to unity and maintains the desired amplitude. Now, this is what we are saying. For oscillation to start, now we introduce the VCC, which is the the battery or whatever that is powering the amplifier or the oscillator circuit. Now, at time equals T0, oscillation begins. The first we come out, if you look at figure 6b, you see that at T equals T0, the amplitude of the signal produced is small. We say that this output is fed back and further amplified. It gets to the second, amplitude we are saying there. That is fed back and it gets back. So we say that at that initial time, the gain must be greater than 1. So if you look at that plot 6b, you see the range where the closed loop gain is greater than 1. The signal continues to build up. When it is greater than unity, it continues to build up until it gets to the desired frequency, level, both amplitude and that is required. Then the system is made to come down to unity 1 and remain at 1. When it remains at 1, you see that the signal produced will be the same and uniform. So see that is what happens. Now, how does this oscillating circuit maintain this? Let's see. So the oscillators with the RC feedback circuit that can maintain that operation we have seen include the Wien bridge oscillator, the twin T oscillator, and the phase shift oscillators. Generally, the RC feedback oscillators are used for generation of frequencies less than 1 megahertz. And the Wien bridge is the most widely used oscillator in this range of operations. Now, what we have done is to see how oscillation builds up. We will, in our next lecture, look at specific oscillators because there are so many of them. Like we have just seen here, the Wien bridge, the twin T oscillators are all examples of RC oscillators that produce less than 1 megahertz of frequency. So, in our next lecture, we'll be looking at how these oscillators do this build-up and oscillate. So we look at the Wien bridge and we will look at the ones that make use of LC. When we say LC, we're talking of inductor, capacitor, feedback circuit. When we say RC, we are talking of resistor, capacitor circuit. So under the LC feedback circuit, we'll be looking at the cockpit oscillator. So join us in the next lecture and get how these two oscillators, the Wien bridge and the cockpit, represent the RC and the LC feedback circuits in terms of oscillations. Thank you for listening.